Okay, let me share my screen. All right. So today, well, before we get to the topic for today, let me just I've posted this earlier this morning, um, basically indicating that the test number 3 is a take-home test. I've already posted it in Canvas under the files link in a folder labeled test. And there are some requirements, of course, that you need to um, meet in order to submit this assignment in Canvas. And then just to confirm, so we're all on the same page, that your final exam is on May 5th. I'm just looking at the college schedule just to make sure I'm telling you the right thing. So this is CHM 102540. So May 5th at 11 a.m. to 1 p.m. That is basically your final exam date and time. All right. Same room, 107. And as I was saying earlier to somebody who asked me, the reason why I'm doing this, of course, is because the testing center is swamped apparently, especially during the final period. So that's why we're doing the test in-house or in the classroom. Now, if you're not able to come during that time for whatever reason, then please contact me and then we can make arrangements, all right? More than likely, you'd have to do it during my office hours. Okay, so that's basically where things are, all right? Okay, so with that said, let us get into assignment number 14. And basically this deals with, hold on, let me just check something here. Okay, deals with a couple of things. The first of which is this whole concept of vapor pressure and how it relates to the boiling point. So just to give a brief recap, I'm going to get to the PowerPoint here, which basically, oh, somebody's saying something. Let me see. Oh, it's not in files? Okay, let me check. Let me check. I thought I uploaded it. Um, okay, files, and then test, and let's see here. Oh, yes, it's there. Test number 3, spring 26. It's right here. Um, Hold on, let me see somebody else. Oh, you're talking about assignment 14. My bad. Okay, I thought you were talking about the test. Okay, my bad, my bad. Um, okay, assignment number 14. Okay, I'm sorry about that. So let's publish that now. Okay, so it's now there. All right. Okay, so as I was saying, the first question or first set of questions is dealing with the relationship between the vapor pressure and the boiling points. Um, so let me briefly recap in the PowerPoint some definitions. So let me talk about the boiling point. All right, what's the boiling point of a liquid? The boiling point is the temperature at which the vapor pressure of a liquid is equal to the external pressure above the liquid. Now, let me just say this. Every liquid, if you have a liquid in a closed system, let me see if I have a diagram here. Okay, I don't. Let's say you have, okay, where's my pen? Oh, here it is. Let's say you have a liquid in a beaker or some sort of container, right? And so this is your liquid here. And let's say you have a covering here, which basically seals everything inside the beaker, right? What you're going to have is that some of the liquid molecules will move into the space here to form a vapor, right? And that will continue until it reaches a certain point. In fact, it's going to reach a point where you have molecules leaving the liquid and going into the gaseous state or vapor state. And at the same time, you're going to have some of the vapor molecules going back to the liquid state. So you're going to have this back and forth until the amount of gas or vapor here will be constant. And because it's a gas up here above the liquid, it exerts pressure. So we call that the vapor pressure, right? So the vapor pressure is basically the pressure of the vapor just above the surface of the liquid in a situation like this where the system is closed, all right? So that's the vapor pressure. Now, what will happen is that if you increase the temperature, let's say you heat this here, right? If you increase the temperature, what will happen is that more of the molecules from the liquid state will move into the vapor state. So therefore, as you increase the temperature of the liquid, the vapor pressure will increase as well, right? And that's where the definition of boiling point comes into play, because if you increase the temperature such that the vapor pressure is equal to the external pressure, then basically that's where you're going to get to the boiling point of the liquid. So that's why we have this definition right here. The boiling point is the temperature at which the vapor pressure is equal to the external pressure. And then there's another definition known as the normal boiling point, which is the temperature at which the vapor pressure will be equal to the atmospheric pressure, right? So that would be the temperature, that temperature, I should say, would be the normal boiling point, all right? So basically we can say that the higher the vapor pressure, the lower will be the boiling point. All right. And the next slide I'm going to show you. Well, before we get to that slide. So I was about to show you the graph, but this is the data which is used to plot the graph I'm about to show you. So what this is showing you is the vapor pressure of different liquids, water, ethyl alcohol, and ethyl ether at various temperatures. So what they did for each of these liquids is that they start off with 0, increase the temperature by 10 degrees each time, and correspondingly measure the vapor pressure of the liquid as the temperature increases, right? So this is basically the data that is going to be shown on the graph on the next slide. But before we do that, remember we talked about the normal boiling point. The normal boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. And the atmospheric pressure is about 760 torr. So in the case of water, the vapor pressure of water would be equal to the barometric pressure or the atmospheric pressure when the temperature is 100 degrees Celsius, right? So that's why we say that the boiling point of water is 100 degrees Celsius. Now, this is some other data I'm going to refer to later on. So let me just skip that and move on to this graph. This is the graph I want to get to. So this graph is basically plotting the data that I showed you in the table 2 slides ago, all right? It's a plot of vapor pressure on the y-axis and the corresponding temperature on the x-axis, right? And this line here is the data plotted for ethyl ether. This line is for ethyl alcohol, and this line is for water, all right? So basically, if you take, for example, ethyl ether, if you start at just above 100 degrees Celsius, I'm sorry, if you start at minus 10 degrees Celsius, then the vapor pressure is just above 100 torr. And then as you can see, as the temperature increases, the vapor pressure correspondingly increases. And you see a similar trend, even though it starts lower here, but you see a similar trend for ethyl alcohol and for water, all right? Now, remember we talked about the atmospheric pressure. So what was done here was that a line was drawn right across here, which basically shows you where 1 atmosphere is, all right, which is 760 millimeters mercury, right? So if you want to find out what the boiling point of ethyl ether is, based on this graph, based on the data that is used to generate this graph, then what you'd have to do is draw a line from 1 atmosphere, which is 760 torr, to where it touches the line, and then drop a vertical line down, and where it cuts the x-axis, that would be the boiling point of ether under normal conditions where the vapor pressure is 760 torr. All right. And it shows here that the normal boiling point of ether is 34.6 degrees Celsius, right? And then if you were to do the same thing for ethyl alcohol, same thing, you draw a line here, drop the vertical down, you see that the boiling point of ethyl alcohol is 78.4 degrees. And then if you do the same thing for water, the boiling point is 100 degrees, right? So one can clearly see that you can calculate or determine the boiling point based on these plots, all right? And as I said before, what you'll find is that the vapor pressure and the temperature at which a liquid boils is kind of like an inverse relationship, right? So the lower the vapor pressure, the greater would be the boiling point, right? So we see that clearly in the relationship between ethyl ether, ethyl alcohol, and water, all right? Let me see here. Now, you can not only find the boiling point, or I should say the normal boiling point, which would be the boiling point under the conditions of 1 atmosphere pressure, but you can actually find the boiling point under any pressure, right? Not only at the atmospheric pressure. And one example is shown here. In the case of ethyl alcohol, let's say you want to find the boiling point where the vapor pressure is 500 atmosphere, I'm sorry, 500 torr, then you do the same thing as you did up here. You draw a horizontal line at 500 to where it cuts or touches the curve for ethyl alcohol, and then you drop a vertical line down, and where it cuts the x-axis, that would represent the boiling point of ethyl alcohol, which is 68 degrees Celsius. All right. You can do the same thing for ethyl alcohol at 700, right? Drop the vertical down, and the boiling point is 77 degrees Celsius, right? So basically, you can determine the boiling point at pretty much any external pressure if you're given a plot of this type. So reason why I'm going through all that is because that is necessary for you to answer the first question in the assignment, which I'm going to bring up now. Okay, so this is a question here. Let me make it a bit smaller. This question says, the vapor pressure of a gas above its own liquid depends on the temperature. The boiling point or the temperature at which bubbles of vapor form within a liquid depends on the vapor pressure and atmospheric pressure. And the following graph shows the vapor pressure curves for two substances, A and B. All right, so this is a graph right here. So the first question is asking, what is the vapor pressure of A at 35 degrees Celsius? So what you'd have to do is identify where 35 degrees Celsius is on the x-axis, which is right here, about here. This is where 35 is. And then you draw a line, a vertical line, where it cuts the curve for A. And that looks like to me that the corresponding vapor pressure, which is measured in kilopascals this time, is 26.7 kilopascals. All right, and that's it. Okay, any questions about this? Any questions? Okay. The next question is, what is the vapor pressure of B at, again, 35 degrees? So in the case of B, this would be the point right here. It's the same temperature as in the case of A, but this time we're looking at where it touches or cuts the curve for B. And then we have to draw a horizontal line to see where it cuts the y-axis. And from the look of things, it looks like about halfway between 0 and 13.3. So what is the half of 13.3? Divided by 2. Okay, so I got 6.65 when I calculated that, 6.65. And again, this would be kilopascals. All right. Okay, any questions about this? Any questions? Any questions? Okay, let me clear this here. Um, okay, how am I going to do this? Because I'm going to need to refer to the graph in order to answer the other questions. Okay, this question is asking at what temperature is the vapor pressure of a 106.6 kilopascals, right? So basically, we have to identify 106.6 kilopascals, which is right here. All right. And the question is asking for the vapor pressure of A. All right. So basically, this is 106.6. So that would touch the curve here. So now we have to drop a vertical line down to where it cuts the x-axis. So this would be admittedly an estimation. So this looks like, would you say this would be 75 degrees Celsius? It looks like 75 degrees Celsius to me. So that's what I'm going to write down. So here, I'm going to put the answer being 75 degrees Celsius. All right. And then the question is asking for the vapor pressure of B at this temperature. So let me clear this again. So, oh, at this temperature. Oh, my bad. So basically, I shouldn't have, in fact, let me see if I can bring this back. Okay. So they're asking for the vapor pressure of B at this temperature. So basically, this is what we had before. So basically, the question is asking now for the vapor pressure of B. So in other words, where the line cuts the curve, we draw we don't even have to draw. There's a line right here. So the answer here would be 26.7. All right. So let me clear this here. Scroll down. So the answer for D would be 26.7 kilopascals. All right. Okay. And then it says at what temperature is the vapor pressure of B 106 kilopascals? So let me go back up here. So they're asking for the B temperature when the vapor pressure is 106 kilopascals. So let me clear this here. Okay, so again, we don't have to draw the line because the line is provided for us. So all we have to do now is drop a vertical down. And that vertical, by my estimation, is about there. What do you think this is? It's closer to 120 than 110. So what do you think that could be?
118.
Okay, I'll go with that. So the answer for which one is it? E, right?
Yeah.
Okay, so 118. I'm going to say approximately because, of course, we have to estimate it. All right. Now, F is asking, what is the normal boiling point of A? Okay, so the normal boiling point would be the boiling point when the pressure is 1 atmosphere. All right. So let me scroll back up to the graph. Now, the boiling point in terms of, I'm sorry, the pressure, 1 atmosphere is equal to 101.325 pascals. I'm sorry, 101.325 kilopascals. So we really have to do an estimation on this one. Because 1 atmosphere, let me write this down, 1 atmosphere is equal to 101.325 kilopascals. So we have to estimate where this is on the y-axis. So, let me see here. All right. By my estimation, 101.3, it would be about here. What do you think? Let's go with this, all right? So we draw the horizontal line, and the question is asking for the temperature for which one? Is it A or B? A, okay. The boiling point for A. So we drop the vertical down. Okay, so this looks like what? What would you say this is? Would you say that's about what? 74?
Yeah, probably.
I go, huh?
Yeah, 74 Celsius probably.
Okay, so let me scroll down and put 74 for the normal boiling point of A, 74 degrees Celsius. And they're asking the same thing for B. So let's scroll back up. So in the case of B, oops. Okay, in the case of B, we would have to continue the horizontal line across. Oops. And then drop a vertical down. Okay, so what do you think this is? Uh, it looks like it's slightly above 115. I would say 116. So in the case of B, 115 would be the normal boiling point. Oops. Okay, so I'm going to say 115 degrees Celsius. Okay. Um, in the case of H, it says at what temperature would A boil in Denver where the atmospheric pressure is 93.3 kilopascals, right? So let's scroll back up. Well, let me clear this first. So it says 93.3 kilopascals. That's what we're looking for on the y-axis. So they're asking what would be the boiling point of A, and that's, fortunately for us, there's a line here which represents 93.3, and then there's another line where you drop the vertical, so the answer would be 70 degrees. So the answer for H is 70 degrees Celsius. And then in the case of G, what would be the atmospheric pressure have to be in order for B to boil at the same temperature as as you gave in your answer to number 8? I think this is a typo. This should be H, right? So basically what they're asking for is um, what would be the atmospheric pressure have to be in the case of B to boil at the same temperature, which would be 70 degrees. So I have to scroll back up and look for where 70 degrees is on the x-axis, which is here. We draw the line. Well, a line is provided there. So what we have to do is draw a horizontal line to see where it cuts the y-axis. And, oh, okay. So this one, we have to do some estimation here. Uh, um, it looks like it's closer to 26.7. Let me see here. Okay, I'm going to say about 21. I'm going to say 21.0 degrees Celsius, right? Um, and again, this would be an estimation. So I'm going to write down here approximately 21.0 degrees Celsius. Can't say for sure, all right? Okay, that would be the answer for G. Let me scroll down here. Okay, so that's basically all the questions associated with that graph, all right? Any questions about any of these? Any questions? Any questions? Okay, so let me move on now to the other questions, which has to do with calculating the amount of heat to change water from one state to another. So of course, we know that water can exist as in a solid state, liquid state, and gaseous state, right? And there are some definitions. In fact, let me go back to the PowerPoint here to talk about certain definitions. So basically, um, we talked about the boiling point. The freezing point is the temperature associated with the equilibrium between the solid state and the liquid state, as you can see here, right? Now, melting is going from solid to the liquid state. Freezing is the reverse process. The temperature at which either occurs will be the same, right? So that's why the term freezing point and boiling point both are meaning the same thing, right? So, basically, if you're at the freezing point of, let's say, water, right, you have a back and forth taking place where the solid would be converted to, hold on 1 minute, the solid would be converted to a liquid, right? So some of the solid will go into the liquid state, and at the same time, um, you're going to have the formation of solid coming out of the liquid state. All right. So basically, things will remain steady. And the term we use for that is equilibrium, right? Where the amount of solid ice and water in the liquid state remains the same, even though you have the back and forth occurring. All right. Okay, so let me talk about what is called the heating curve. The heating curve is basically a graph where we plot the temperature on the y-axis and the amount of heat added on the x-axis, right? And I think this is the heating curve for water, but this can be applied to different substances where the values of the melting point and boiling points will be different, right? So if we start from here, below 0 degrees, where you'll be dealing with solid ice, as you increase the temperature, or I should say, as you add the heat to the system or to the ice, the temperature will increase until you get to the melting point. Now, at the melting point, of course, you're going to have the conversion of the liquid, of the solid ice to the liquid water, right? As long as you have both present in the mixture, the temperature will remain steady, and that will be the freezing point, and that is what is shown right here. This flat line here shows that the melting point is 0 degrees, and it will remain steady as long as you have ice present. Now, when all the ice has melted, what will happen now is that the water will start increasing in temperature. And that's what this slope is representing, right? So from C to D, you're going to have the melting, I'm sorry, you're going to have the increase in temperature of water, right? And then when you get to the boiling point of water, which is 100 degrees Celsius, then what will happen is that you're going to have the conversion of the liquid water to the water vapor, which is a gaseous state, right? At that point, the temperature will remain at 100 degrees. So as long as you have the combination of water and water vapor present, you're going to have the temperature remaining at 100 degrees until all the liquid water will be converted to the water vapor. Whoops, sorry. And when that happens, then basically just going to have steam. And as you increase the temperature, or as you add heat to the steam, the temperature increases, right? So that's basically what is happening as you melt ice from 0 degrees Celsius, take it through the changes until you get to steam at above 100 degrees Celsius. All right. Now, what we're going to look at is how we can calculate the energy at each stage, right? We can calculate the energy here, the energy required to do this, the energy at this slope here, and the energy here, and then finally the energy here. Now, in order for us to do that, there are some constant values that you need to have access to. You don't need to memorize them because I would have to provide that for you. So let me go back to a table that I skipped over. Okay, so this table here is what you're going to need. In fact, I'm just going to focus on the very last line right here, right? These are the values associated with water, right? So, the boiling point of water is 100 degrees. We already know that. The freezing point of water is 0 degrees. Now, there's a term called heat of vaporization, right? The definition of the heat of vaporization, it's the amount of heat needed to vaporize 1 gram of water, all right, in the liquid state. So you're starting from 1 gram of liquid water and converting that to vapor. So the amount of heat required is given both in joules per gram and calories per gram. If I stick to joules per gram, it's going to be 2,259 joules per gram, right? So for every gram of water, right, to convert it to vapor, this is the amount of heat that you're going to need, all right? Another term or another definition that you need to be aware of is what is called the heat of fusion. The heat of fusion is the amount of heat needed to melt 1 gram of ice and convert it to liquid water. So again, the values are given in joules per gram and calories per gram. If I focus on joules per gram, this is the amount of heat, 335 joules required to melt 1 gram of ice and convert it to water, all right? So these values you're going to need. In fact, I'm going to, since I don't want to forget these values, I'm going to write those values up here. So heat of vaporization is equal to 2259 joules over gram, and heat of fusion is equal to 335 joules per gram, all right? So we're going to need those values. So let me clear these. Let me clear that. Okay. Okay, so let me get out of this here. And let me go to the assignment. And, oh, I can hardly see these numbers that I just wrote. Hold on. Oh, I'm trying to, okay. Let me write it down here. Heat of vaporization is equal to 2259 joules per gram. And the heat of fusion is equal to 335 joules per gram. Okay, and what I'm going to do is erase this here. Okay, so let me go back to, okay. So this question is asking, hold on. All right. Okay, so this question is asking, how many joules must be added to 10 grams of water to raise the temperature from 10 degrees to 15 degrees. Well, this question, this type of question you would have done, or you should be able to do based on what we covered in chapter 13. Basically, the equation you're going to use is Q is equal to M times C times delta T. Remember that equation, right? So Q in this case would be equal to M, which is 10.0 grams, times C, which is 4.18 joules per gram degree Celsius, times the change in temperature, which would be 15 degrees Celsius minus 10 degrees Celsius. And that's it. So let's see what this gives. 10 times 4.18 times 5. So, well, this part here would be 5 degrees Celsius. So the final answer would be rounded off to 1 sig fig, which is 200 joules. All right? And that's it. And that's how you would do question number 2. All right? Any questions about this? Any questions? Any questions? All right. Let me erase this here. And let me scroll down. Okay, now the next question is similar. I won't do it. I'll leave that for you to do. Again, it's asking for the amount of heat. It gives you the mass of gold. It gives you the temperature, initial and final, and it gives you the specific heat. So I'm going to leave that for you to do. Let me go to number 4. Number 4 says how many joules are released as 10.0 grams of steam at 100 degrees Celsius cools to produce water at 25 degrees Celsius. All right, now here's the thing. You have to think of the changes that would take place as steam, H2O gas, goes to H2O at 25 degrees Celsius. So according to the question, the temperature is 100 degrees Celsius for the steam, right? So when you cool it, what will happen is that H2O gas, which is steam, will be converted to H2O liquid, right? And the temperature is going to be 100 degrees Celsius as well, right? Then what's going to happen is that the liquid, upon further cooling, will have the temperature decrease from 100 degrees Celsius to 25 degrees Celsius, all right? So basically, we have 2 steps involved. The first step would involve release of heat as you go from gas to the liquid. So I'm going to call that heat that is released Q1, right? And then the release of heat as you go from 100 degrees Celsius to 25 degrees Celsius, I'm going to call that Q2, right? So basically what we need to do is find out what Q1 is and what Q2 is, and then add them together to get the total amount of heat, all right? We need a mass, which is 10 grams as well, all right? So let's go about it. I'm going to do it up here since there's space up here, right? So Q1, let's calculate Q1 first. Q1 would be equal to the mass of the steam, which is 10.0 grams, multiplied by the heat of vaporization, which is 2259 joules per gram, all right? So that would be equal to 2259 times 10, rounded off to 3 sig figs. So according to my calculation, that works out to be 2.26 times 10 to the 4 joules, right? And then for Q2, that would be the heat released when the water is cooled from 100 degrees Celsius in the liquid state to 25 degrees Celsius in the liquid state. So the equation that you're going to use for that is this equation that we mentioned before, M times C times delta T, right? M is 10.0 grams. C is 4.18 joules per gram degrees Celsius, and delta T would be the change in temperature, which is 100 degrees Celsius minus 25 degrees Celsius, right? So this part here, of course, works out to be 75 degrees Celsius. So let me do the rest. 10 times 4.18 times 75. And according to my calculations, when rounded off to two sig figs, that works out to be 3.1 times 10 to the 3 joules, which is the same thing as 0.31 times 10 to the 4 joules. So basically, we're going to add this to this, right? So I'm going to continue down here, 2.26 times 10 to the 4 joules plus 0.31 times 10 to the 4 joules. So let's see what that gives. So according to my calculation, this works out to be equal to 2.57 times 10 to the 4 joules. And that would be the answer. All right. Okay. Any questions about this one? Any questions? Any questions? Okay. Let me see. Oh, that's the last question. Okay, so that's pretty much all I have for you today. What I'm going to do is create a Dropbox for this. So this would be assignment number 14. And let me see here. Okay, I'm going to let it be due on Friday, which is the 1st. All right. So let me do this. Okay, so now you'll be able to upload your completed assignment number 14 into Canvas. And I see somebody is saying something in the chat. Let me see here. Okay, somebody's asking, so how do we get our 20% gain on the final? I missed that. I'm afraid you did if you're talking about the 20% given to those persons who attended that panel discussion. So yes, I'm afraid you missed it. All right. Okay, any other questions or hold on, let me see somebody else's. Oh, okay. Any other questions about this or about anything else as far as the course is concerned? If not, that's pretty much it I've got for you today. So I'll be available for office hours tomorrow's what, Wednesday. I'll be available at the Ocala campus, but of course we can communicate via Zoom. I'll be here well, not here, but at the Citrus campus on a Thursday from 1 to 4. And again, I'm going to be at the Ocala campus from 2 to 5 on Friday. All right, so those are my availability times if you need to ask me any question about anything in relation to this course. Okay, so that's pretty much it. Yeah, that's pretty much it. All right. So if there are no questions, I'm about to sign off now. So I'll see you guys again, just to confirm. Your final exam will be on Tuesday, May 5th from 11 to 1 p.m. in room 107. All right. Okay. So that's pretty much it. I'll see you guys, I guess, during your finals. All right. So